We will be taking questions at the end of the talk, but right now I wanted to present first Mathilde. Mathilde is a physics PhD student in the Geometric Intelligence Lab at the University of California, Santa Barbara, where she develops novel deep learning methods leveraging geometry and topology. She harnesses these models to study relational data with a special focus on full body human movement. Her experience with human movement is informed by her experience as a professional dance choreographer and as a data scientist in the sports analytic industry. And Mathilde obtained her bachelor in honors physics from McGill University and was recently awarded Canada's postgraduate doctoral fellowship. We're super excited to have you, so please take it away.
Thank you so much for having me. I'm really, really excited to be here. My name is Mathilde. Thank you for the introduction. I am from UC Santa Barbara, and today I will be telling you a little bit about a recent preprint that my lab and collaborators just put out called Beyond Euclid. It's meant to be an illustrated visual short guide to geometric, topological, and algebraic structures. This work is in collaboration with a bunch of really awesome people who I've listed here, and let's dive into it. So my goal will be to provide a guide that can help us make sense of the enormous amount of publications that are coming out in AI. This figure is from 2022, so it's only gotten worse since then. It's basically impossible for any of us to keep up with this, and it can make it really difficult to know what people are working on, how we can best contribute and best focus our efforts. So the field of geometric and topological AI is no different. We have a ton of really cool papers that have come out in the recent 2 years or so, and it can be really hard to know what is common among the works, what's different, what are open questions that are left to answer, and how we should focus our research efforts. A small disclaimer that there are a really good set of educational works out there that will tell you everything you need to know about these fields, a full descriptive mathematical guide to geometric deep learning, topological deep learning, algebraic deep learning, and so on. But our goal here is to give something that is meant to be more of a companion resource, something that is much shorter, very visual, kind of a cheat sheet on the field that you could sort of print and hang next to your computer, unlike these sort of 100, 200 pages guides that exist out there. So different purpose. Okay, so let's answer the first question that I just asked. What is common across all of these works? Well, we in our guide say that what is common is the appearance of non-Euclidean structures in our data. So specifically, I'm going to present 3 classes of non-Euclidean structures that appear in these works. So non-Euclidean topology, non-Euclidean geometry, and non-Euclidean algebra. So I'm defining these pretty abstractly at a high level right now, and later we'll see how they appear concretely in the literature. We call these non-Euclidean structures because they generalize the Euclidean space that we see on the left. So in the first row, we are discretizing this Euclidean space because we're going to be talking about discrete topology. So when I say generalizing discrete Euclidean space, that can look as simple as a graph, right? I have now introduced relationships between my points and created a non-regular grid. And then I can get a little bit more fancy with it and introduce more complex higher order relationships, such as faces, right? Like in a cellular complex, we're introducing faces in between edges, or the set-wise relationships of a hypergraph that allow for any number of nodes to be connected by an edge. Okay, so that's non-Euclidean topology. Now moving on to geometry, in this case, we are taking the Euclidean space back in its continuous form and adding curvature to get manifolds, which are curved generalizations of Euclidean space. So for example, the sphere has positive curvature, the hyperbolic space has negative curvature, and then we can create more complex manifolds possibly in higher dimensions, not necessarily just in 3 dimensions. Okay, moving on to algebra. Our third class of non-Euclidean structure considers how the elements of a space, whether that be a Euclidean space, a geometric space, an topological space, transform under groups of transformations. So if I have a structure in Euclidean space, for example, this vector, and I allow it to transform under, for example, a translation or a rotation, I have added algebraic structure to my domain. There are really a whole lot of group transformations that exist out there, but I think you get the idea with these few examples of rotation and reflection, for example. Okay, so now we have our 3 classes of non-Euclidean structure that will allow us to categorize literature into a visual framework. So our key colors here are pink, orange, and blue. And moving on to our second question, we can now ask, what is different in the literature? How do we sort of distinguish these different works? And the way I will do this in this talk is distinguishing works by how non-Euclidean structures appear in the data that the works consider, the machine learning methods that they consider, and or the deep learning methods that they consider. So let's start. And yeah, so overall, that's how our guide to non-Euclidean structures is organized. Data, machine learning, deep learning. So starting with data, let's go back to Euclidean structure for a little bit and just talk about how we can distinguish 2 main categories of data. Data as coordinates in a space and data as signals, going from a domain to a codomain. So a data as a coordinate is basically just a point. In Euclidean space, it's a point, x in Rm. An example of this would be, for example, the measurements, the height and the width of a flower from the well-known iris dataset. This is a point in R2. When we're talking about signal, we're talking about x going from a domain Rm to a codomain Rm prime, which might sound a little bit abstract, but an example of this is an image, right? So in an image, our domain here is R2, and at every single point in R2, we're assigning a vector Rm prime, which in this case could be a scalar that tells us what the grayscale is, or it could be RGB value, for example, in R3. Okay, so we have our data as coordinates and our data as signals in Euclidean space. Now, how can we generalize these to non-Euclidean spaces? So coming back to our coordinate case, our coordinate category, let's consider an x point in Euclidean space. What happens if I add non-Euclidean geometry? Well, now I will have a point on a manifold, right, which is a generalized non-Euclidean domain. And an example of this would be the geocoordinates of anything that happens on the surface of the Earth, because the surface of the Earth is curved. So for example, the coordinates of a storm. Okay, next, what happens if I add topology? Well, in this case, we're going to discretize our Euclidean space and end up with, for example, a graph, right? Our point is actually a node in a graph. An example of this would be a person in a social network. And lastly, if we add algebra, well, we are equipping our Euclidean space with some group action. So this could look something like changing the measurement units of how we are changing or how we are measuring the flower. So there you have it. These are sort of 3 examples of how we can introduce non-Euclidean structure into our data. Now we can go sort of 1 level deeper and equip topological and geometric spaces, so our left and right columns, with algebra, with a group action. So this could look like changing the node indexing, node permutation in a graph, or changing the spherical coordinates, for example, of how we are measuring the coordinates of the storm. Okay. Now that we've done coordinates, let's consider signals. So coming back to our original Euclidean example of a grayscale image, what happens if I add geometry? Well, this could look like generalizing the domain of my signal to a non-Euclidean space, such as a manifold, right? So now in this case, it could be the Earth, which is the manifold, and at every single point of the Earth, we assign a scalar value such as temperature. So this is a signal that is defined on a manifold. And then we can do the opposite, where we, instead of generalizing the domain to be non-Euclidean, we generalize the codomain to be non-Euclidean. And this is what happens in diffusion tensor imaging. So in this case, our domain is R2. And at every single point of R2, we are assigning a covariance matrix, which is a geometric object. Okay, now we can do both, right? And generalize the domain and the codomain to be manifold valued. And this is what happens in air traffic covariance, where at every single point on the surface of the Earth, we're assigning a covariance that describes the air traffic. Okay, now we've done the geometry side of things. Let's consider the topology side of things. So we can generalize the domain of our signal to be a topological domain. So for example, a graph. And in this case, you could think of the human body, where the joints on the human body are each part of a graph, and their feature that we're considering is, for example, the Cartesian coordinates that describe where they are in space. So that would be a graph going to R3. And we can also assign manifold valued features to each of the points on our graph. So this could be, for example, assigning rotation to each of the joints of the human body. Okay, so now we've considered geometry and topology. What about algebra? So if I'm adding non-Euclidean algebra to my data, that comes down to equipping my space, my domain space, whether it's topological, Euclidean, or geometric, and equipping that with some group action, such as permutation or rotation. I can go one level deeper and also equip the codomain of my signal with group action. So I'll just leave that there. Okay, so now that we've done data, I hope that wasn't too much of a mouthful, we can consider how these structures appear in machine learning. And my goal here is to go over two sort of very canonical main problems of machine learning, so regression and dimensionality reduction. And we're going to build up tables that can help us understand what is common and what is different amongst a bunch of different models that use non-Euclidean structure. So starting with regression, as we did with data, we're going to start with the Euclidean case. On the left, we are seeing how we are categorizing the input and output spaces of the model. So in this case, we're only looking at one row of the table, which considers an Euclidean input in Rm and a Euclidean output Rm prime. And then we are also going to consider how the regression model actually works, right? Is it a linear model? Does it fit basically just a y equals mx plus b to our parameters? Or is it parametric? Does it allow for more parameters to be involved, but they're still fixed? Or finally, is it non-parametric? So does not fix any sort of parameter at all. We're also going to separate things by Bayesian and non-Bayesian. Okay, so in the linear case, very simple. We're all familiar with linear regression, I hope. Parametric case, you can think of polynomial regression. And then non-parametric, you get into kernel stuff, random forests, and so on. And then we can generalize these to the Bayesian methods, which will integrate prior probabilistic distributions with the observed data, allowing for us to update our knowledge about the parameters in light of new evidence. Okay, so this is just like a very basic overview of regression. Now let's get to the fun part. Let's consider what happens when we introduce non-Euclidean structure. So I have now added to this table two rows. One row that considers models going from one-dimensional Euclidean space to manifold M prime, and one row that considers going from one-dimensional or multi-dimensional Euclidean space to manifold M prime. Quick note that when we are dealing with manifolds, linear regression no longer works. This is because the addition operation on a manifold is not well defined. We work with geodesics instead of working with lines. So we're going to talk about geodesic regression instead of linear regression. Okay, so in the non-Bayesian case, the one-dimensional Euclidean input case, you can see sort of the extension of our first row into manifold space. And we can do the same for Bayesian models. And then when we get to the multi-dimensional Euclidean input, there's actually some open questions. So this is an example of how our framework kind of allows us to identify places that the literature has not yet proposed works for. So if you feel like being the first person to perform parametrized regression on multi-dimensional Euclidean data going to manifold data, well, you could. Okay, we're going to add one last row to this table, and we're running out of space, so I've sort of overlapped the rows, where we are considering the input space to be non-Euclidean. So in the first row here that I've added, it's non-Euclidean going to Euclidean, and in the second row, everything is non-Euclidean. And in this case, we deal with parametric and non-parametric regression exclusively, and a few works have been proposed for these cases. Okay, so that was regression. This is our table that we have just built together. And now we are going to do exactly the same thing for dimensionality reduction. So starting with the Euclidean case, we want to consider data that is Euclidean, that is going to be dimensionally reduced to latents that are also Euclidean. So in dimensionality reduction, the goal is to transform high dimensional data from Rm, for example, to lower dimensional space, which we'll call the latent space, Rm prime. We will consider various combinations of Euclidean and non-Euclidean data, just as we did earlier, and we'll also consider the different kinds of dimensionality reduction. So in this table, we are only going to consider models that use a decoder. And at the end, we'll look at models that don't use a decoder. Now, when a model uses a decoder, what kind of decoder is it? Is it linear or geodesic in the manifold case? Is it parametric or is it non-parametric? And then in the sub-rows, these three sub-rows that we have, we'll consider if the model does not compute a prior distribution, which is just the solid blue dot. So this means in the case, so, and then the second sub-row will be that we do compute a posterior distribution. And this means computing an uncertainty on the latents y associated with the data points x. And finally is the model Bayesian, which is this sort of fuzzy orange line. So we can fill in our table. The first line should be pretty familiar to everyone. Principal component analysis. An autoencoder is parametric, and principal curves is non-parametric. In the principal curve case, instead of a encoder, we use a sampling mechanism, but they all use a decoder. Okay, moving on to the posterior distribution case, we are generalizing these models a little bit. So we get probabilistic PCA, we get a variational autoencoder, and probabilistic principal curves, for example. And then finally, the Bayesian extensions of all of these. Okay, so this is our Euclidean case. Now, what happens when we introduce non-Euclidean structure? Again, we're going to add two rows. One row that is going from manifold data to one-dimensional Euclidean latents, and one row going from manifold data to multi-dimensional Euclidean latents. And as you can see, there's models that span all of these categories. You can consider, for example, the geodesic one-dimensional case is a special case of other models. And again, we're seeing this use of sampling instead of an encoder in the right column. And then as we get further down, we see some open opportunities, models that have not yet been proposed. And that concludes for these two rows, going from non-Euclidean to Euclidean. And now we're going to consider going from Euclidean to manifold valued. So we're getting a little bit fancy here with these models. And as you can see, the years, the dates that the models came out are getting a little bit older. And finally, in the case of going from a manifold to a manifold, that's just an open problem. And then finally, as I promised earlier, I mentioned that all of the models in the table would have a decoder. These are the models that do not use a decoder. So there's, again, a variety here of data spaces being used, right? Euclidean to Euclidean, Euclidean to manifold, manifold to manifold, and so on. So there it is. That is our second machine learning table of dimensionality reduction, which brings me to part 3, deep learning. So let's talk about non-Euclidean structure in deep learning layers, starting with the most famous layers of them all. My goal here in each row will be to show you one layer, right, of a neural network that you might be familiar with. So in the perceptron case, which might be the most well-known neural network, we are sending data from Euclidean space X. Specifically, we're sending a point, a coordinate, from Euclidean space Rn all the way to Euclidean space Rn prime. In the convolutional neural network case, we're sending a signal, right? Not a coordinate. We're sending a signal from Rn to Rn prime to Rm to Rm prime. And you'll notice these arrows, which are indicating the fact that the convolutional neural network equips its data spaces with group actions. Okay, so what happens when we want to introduce non-Euclidean structure into our domains? Well, in the perceptron case, we can consider a layer output, which is manifold valued, right? Or we can consider a domain, we can consider an input space to be manifold valued, or we can consider both to be manifold valued. And then when we're talking about introducing non-Euclidean algebra, we could consider equipping each space with a group action, which will lead to this important property called equivariance. So you might have heard about equivariant neural networks. That's what this does. Okay, so moving on to the signal column on the right side. Now we could, for example, generalize the domain of our output signal to be manifold valued and equip it with a group action, GP. We could also, so this is kind of interesting, actually, the regular group convolution neural network published by Taco Cohen in 2016. So the first layer of this model sends our signal from Euclidean space to a group GP, a new signal over group GP. And then the second layer of that neural network takes the signal valued over group GP and sends it to a new signal valued over group GP. So this is kind of cool. We're seeing different non-Euclidean generalizations within one same neural network. And then we can do more complicated stuff with homogeneous manifolds, which is what this quotiented by H represents. Okay, so what about topology? Well, coming back to our convolutional neural network with its Euclidean signal, we could, for example, discretize the domain of the signal and end up with a set of points and then do learning over the set of points. And that's what PointNet++ does. .NET++ is still equipped with a group action, which is permutation variance. Now we could additionally add another group action that will transform the codomain of our signal, which is why we're seeing these arrows on the individual features assigned to each point. We could also introduce relationships between our grid and end up with a graph. This is graph neural networks, which I'm sure some of you are familiar with. And additionally, add more non-Euclidean algebra and get these transformations over the codomain of our graph, those little arrows on the node features. Okay, now what if we're interested in more complicated relationships than just pairwise graph relationships? This is what topological deep learning does. And here we're seeing these more complex, higher order relationships between our nodes. So the first two layers show us simplicial complex, cellular complex domains, omega. The third row shows us a hypergraph domain, omega. And the fourth and fifth rows show us a very general domain, which is sort of a combination of cellular complexes and hypergraphs. We call it a combinatorial complex. And throughout this whole process, we can be equipping both our domain and or our codomain with group action. Okay, so that is sort of an overview of a bunch of different deep learning layers and how they generalize their data spaces to include non-Euclidean structure. And we can make this really big table that has all of the categories. So the writing's a little bit small, but on the left and right side of each table, we've labeled which rows belong to geometry in neural network layers, equivariance in neural network layers, and topology in neural network layers. On the left side is the table that we have just built up together. And on the right side is another table that is in the preprint that you can go look at if you're interested, which considers attention mechanisms. So that's a whole other set of models that have recently been developed that include non-Euclidean structure in their data spaces. Okay. What if you actually want to do this? I'm talking very abstractly right now. I'm talking about these sort of super high level, not very practical concepts. And unfortunately, we do not have time today to go over practical implementation of all of the neural networks in this field. But I wanted to point you to some software that can be really helpful. This is a table that is in the preprint, and it includes the sort of most popular, well-known, well-established packages for geometric deep learning, topological deep learning, and algebraic deep learning. So definitely go check those out if you're interested in getting your hands a little bit dirty. And I will also note that this preprint is meant to be a work in progress. And if I did not include your favorite software package or even your favorite paper, please reach out. Please let us know. You can email any of the co-authors of the paper and we'll be happy to add things. Okay, so another question you might be asking is, well, how do I know where to start if I, for example, have a data set that I'm interested or I have an application that I'm interested in? We have indexed some of the most popular models of each of these categories with attention and without attention, and written down what exactly it is they do, what their structure is, and what data sets they're tested on, as well as what the results on those data sets are. So that can be useful. And with that, we've gone over non-Euclidean structure in data, in machine learning, and deep learning. And I hope that you have sort of gotten a feel for how this enormous and super quickly growing field is organizing itself, and hopefully this can help better contextualize that next paper that will pop out on arXiv in the next hour, I'm sure. So that concludes my presentation. Thank you for listening, and I'm happy to take questions.
Okay, thank you for the presentation. So yeah, I guess everyone can, hold your hand, raise your hand, and I will be calling them out. I can maybe start with some questions. So first, actually, congrats on making, these slides. I was wondering how you were going to fit these long tables in the slides. So yeah, cool. The first question is perhaps related to one of the tables that you have on the guide, where you're talking about benchmarks, and it's a curious thing that most like all the models that actually are showing their the size of the model have at most 10 million or maybe even less parameters. Do you have any insight on why this happens? There is the understanding that some priors like equivariance and so on improve compute efficiency, but maybe there are better insights.
No, absolutely. That's definitely true. It can go both ways in the field. So building in prior knowledge, such as equivariance, right? I wouldn't expect the result of my human motion prediction algorithm to change depending on where I'm oriented in space. So that can definitely help reduce the amount of parameters. On the other hand, think about topological deep learning, where you're adding higher order relationships, right? So you have to add computational cost to consider this sort of combinatorial combinations of possible nodes. So in the field, it can kind of go both ways when we're talking at this high of a level in terms of overviewing the field of math and AI, basically. Why things don't go bigger than 10 million, yeah, I don't have that insight. I would say that there's also practical limitations in terms of what data sets people in academia work with and what hardware people in academia work with. None of us have access to the data set that OpenAI has, for example, and they have geometric priors in their models, right? They've incorporated a lot of geometric deep learning in their work. So I think it's probably also a combination of the resources that academia has access to.
Cool. I have several more questions. I will ask you one more, and then I will leave the word for the other people, and then I'll come back later. Another question that I have, it's related to, in the case of the algebraic priors, having other structures beyond groups, like, for example, categories or even something simpler than a group, like a semi-group, for example. Did you consider reviewing this part on the, because actually categories are, for example, quite linked to topology, right? So
absolutely, yeah. So my funny story, my advisor gave a version of this talk at a workshop at ICML last year, and Max Welling raised his hand and asked the same question you just asked about categories. We did not include categories in the work. I agreed that it would be super relevant, potentially a future iteration of the work. We didn't want to get too mathematical with it in the interest of saying super high level and intuitive and visual, but it would be absolutely relevant to see it through the eyes of category theory rather than just group actions. Yeah.
Cool. Okay, thank you. Now let's, Swarnim, maybe you can ask your question now.
Can you go to the slide about differentiating data sets based on signal and the points?
Just the Euclidean one?
Yeah, like not yeah, this one, the next slide, yes. Data sets as coordinates in space and signals. Couldn't is a measurement of flower can also be considered like from all possible set of heights and width, as a signal of like this particular height and width, the same way this image can be considered like from all possible pixels to like one black and white pixels.
Okay, so yes, the measurement of the flower is pulled from a set of all possible values. But when we're talking about the structure of the data that we're sending into our model, right, the way we are presenting the data, the measurements of a flower is just two numbers, right? It's just coordinates, whatever, x, y, for example, that are height and width. It's just two-dimensional vector. Versus when we're sending in an image, we have to be sending in, well, I guess in reality, we're sending in a discretized version, and it's not all of R2, but we're sending in multiple features for every single point in the image. So I think I understand where you're coming from in terms of how the data is acquired, coming from two similar spaces, but once the data is acquired and presented to the model, the coordinate and the signal are not the same.
Can you expand a little bit? Because even in both in grayscale and the measurement of flower, it seems like we are sending a vector. In the grayscale, we are sending the vector in where each pixel has a scalar associated with it. And in the flower measurement, we are sending a vector where each scalar is associated with one of the features of the flower. So you can't you like also think of these grayscales as like a set of scalars similar to a measurement of flower, which with like some kind of positional embedding instead of a feature name associated with them.
Yeah, no, I think so. But when you consider like the nature of the data, it's the point in Euclidean space. It's one point. We're not considering, for example, a matrix. We're not considering a higher dimensional feature that could be associated to each point.
In like a space of all possible images, won't this particular image also be a kind of coordinate? The same way in the space of all possible measurements of flower, this particular measurement will be a coordinate.
Yeah, that's true.
So like what is the fundamental difference between calling something a signal length or calling something a coordinate?
I think it's just how you describe the data. We could describe the image as a single point in image space, but here we're describing it instead of a point in image space, we're describing what the image is. So maybe just two perspectives on the same thing.
I see. Thank you.
Okay, so Mathilde, maybe you can go now.
Okay, so I am curious about what sort of practical applications are out there for topological deep learning, and I'd like to know if there is any sort of comprehensive survey on that, or at least where I could look out for that.
Absolutely, yeah. So topological deep learning is a super young and emerging field. Recently, a position paper on topological deep learning came out. You can just Google position paper topological deep learning. It's by Papamarcou, Theodore Papamarcou, and they enumerate a ton of possible applications that have seen some interest in TDL. To give you some examples, anything associated with molecules, molecular prediction, molecular design, higher order features in molecules are super important. You can imagine that a molecule that has a carbon ring versus a molecule that doesn't have a carbon ring, those are important features that tell us a lot about the purpose of the molecule. And there's been really great success on molecular data sets in topological deep learning. Another example, to give you something that I'm really interested in, is human motion. When we draw the human body as a graph, we're only considering pairwise relationships between our joints. But when you're moving, you're not thinking, I'm going to move my wrist with respect to my elbow, with respect to my shoulder. That's not how humans move, right? We move with correlated limbs, my leg is a correlated object as a whole. So neural networks that use hypergraphs to describe the human body instead of just a simple graph have seen really good success. So those are just two examples, but definitely check out the position paper for more. In terms of a literature review about topological deep learning, I actually wrote a literature review 2 years ago, and it is very similar to what I just presented in the sense that it's meant to be very visual and illustrated and accessible to newcomers. So that definitely could be something you could check out. It's called Architectures of Topological Deep Learning, something like that, message passing topological neural networks. And you can just Google my name and you'll find it.
Okay, that was very interesting. Thanks a lot.
Cool. So let me ask you another question. This one is about, well, it's related to equivariance, but perhaps it's more general as well. So there are instances, for example, in AlphaFold 3, where they removed equivariant layers and they instead put diffusion, and what they make the network learn the equivariance by data augmentation. And there has been this dichotomy for a while already. And the cases where I've seen it has been done successfully, like replacing equivariance with data augmentation, has been only on symmetries of the Euclidean space. And my question is whether you can do the same with other type of informations in other type of priors, either topological or algebraic or geometric.
Yeah, definitely.
And what?
So by algebraic deep learning, just to be clear, we mean equivariant deep learning. So those are the same. And then topologically speaking, there's really recent research about how we might learn the topological domain that is best for the task. A big, not necessarily a problem, but kind of a caveat of topological deep learning is that you, the practitioner, have to make a decision in terms of what higher order relationships you're interested in considering. And it's very possible that some of those relationships are completely useless and others are very important. So there's a paper called DCM by Bazziloro that they look at how you might learn what higher order relationships you're interested in keeping. And they train a model that kind of picks out the representation in parallel with the main model. So that's very new. There's only one paper, I think, that does this, but I'm definitely interested in that line of work. And then in terms of geometric deep learning, I can't think of something that would learn the representation as it goes. But yeah, hopefully that answered your question.
Yes. Can you mention again the name of the author?
Bazziloro, Battilloro, Claudio Bazziloro. And yeah, the paper is, the method they propose is DGM. I think it's like learning latent topology. That's the title, okay. Something like that.
Yeah, cool. Thank you. So we have a question from Jorge.
Okay, so Mathilde, thank you for your presentation. I just have one doubt because I was seeing your work, and most of the topological deep learning research are most based on until order 2, right? So lifting the data, I think, until triangle. So most of the architecture, so the neural networks that just do message passing in nodes, adds, and triangles, right? I want to ask if it's a limitation or it's not usual to do these things because in higher dimensions, these things don't work.
Sorry, I'm not sure I understand your question. You mean, yeah, go ahead.
Yeah, so for example, in the combinatorial complex neural networks that you guys have in Topo Benchmark and other Gits, you guys use until the Hod Laplacian 2, right? So so you are just using at maximum triangles. So the faces are triangles, right?
Not necessarily, no. So a simplicial complex has triangles as faces as a restriction. A cellular complex, however, can have any possible face as long as it's bordered by edges.
Ah, okay. So it's like an hypergraph, right?
Not quite. So a hypergraph is set type relationships, meaning that any node can be connected to any node in any number. In a cellular complex, there's still this idea of rigid geometric structure in the sense that you have nodes, which can form edges. And then if you have enough edges that they're sort of forming a ring, then you can put a face in the middle of the edge. And the face becomes a new feature, if that makes sense. Versus a hypergraph, where you can also connect multiple nodes at once, but not with a new feature, just with like an additional edge, which we call a hyperedge, if that makes sense. My literature review on topological deep learning gives a pretty good overview to the differences, the subtle differences between these domains, if you are interested in learning more.
Oh, great. It's just that I thought that the incidence matrix you guys used to construct the Hodel-Laplacian use the edge triangle incidence. So no, they can be any incidence matrix.
Yeah.
Okay. Thank you. Great.
No problem.
All right. Then next one is Chuang Chi Shou.
Yeah. So just to make sure, when you say equipping the geometry with group actions, do you mean making the input or output equivariant to certain group actions or something else? Okay.
Yes. Yeah.
Okay. Cool. Then the next person is Sahil.
Hi. Thanks for the talk. One question I had is kind of more of a meta question. Can you use this to learn the objective function that you should be optimizing? Kind of if you were to view the objective function as like this surface in this high dimensional space, but you're not sure which objective function you want to optimize. Could this be used for such a thing?
I think that comes back to the question we had earlier about learning representations on the fly. I think so. I think you could. I'm not familiar with anything in the geometric specific field that does that. But to parallel with the topological field, people are interested in learning the representations on the fly that are sort of optimal for whatever task it is you're doing. But absolutely, I mean, you could think about learning the manifold that best represents your data, and people do that.
I see. Last question I have is, does this approach generally require a lot of data, or like, is there generally a rule of how much data you need in order
That's
to?
a really good question. Yeah, that's a really good question. It varies. Coming back to our first question that we had about number of parameters, it varies a lot on the field. For example, topological deep learning, you're necessarily adding information versus building in equivariance can help you cut out information. But my experience is that you don't need a ton of data. So for example, one of the biggest benchmark data sets in topological deep learning that everyone uses is the zinc molecular data set. And the subset of it, which people often use just on its own, is about 12,000 molecules. So not that much overall.
Got it. Thank you.
Cool. I have a couple of more questions. The first one is actually two questions, but they are quite related. One is whether there is some work on transfer learning from, let's say, a problem with certain topological structure to another problem with a different topological structure, or perhaps with no structure. Whether this has, and related to this is whether there is work on foundational topological deep learning models.
So transfer learning is like an open problem of the field, and something that a recent work that I just put out called TopoTune, I'm really excited about applying to. So transfer learning has been studied pretty extensively in graph neural networks, if you're familiar. And the question is, how can we extend that to non-Euclidean structure, right? How can we extend that to topological neural networks? And that hasn't been tackled sort of with the traditional topological architectures that have come out. A recent work that I just put out called TopoTune builds topological neural networks out of graph neural networks. So it takes a GNN and through some kind of fancy footwork, turns that GNN into a TNN, but with very little software modification and theoretical modification. So that is a future line of work that I'm really interested in, is can we extend the GNN transfer learning field to TNNs now that we have a TNN built with GNNs? And yeah, to answer your second broader question about foundational TDL models, not that I know of in academia. I think there are some companies that are really interested, especially in the pharmaceutical molecular side of things. But I think it's actually listed as an open problem in the position paper.
Sorry,
you were muted.
I got disconnected for a minute. I will check the recordings, whatever you said. I will not make you repeat it. I have one more question, or maybe two. So something that has happened in natural sciences throughout history is that sometimes some new purely mathematical theories have emerged either by a consequence of studying a topic or as a need to study a topic. My question is whether you think or not that something similar will happen by studying the structure of the machine learning architectures of machine learning problems. Either will new math emerge? So the question is, do you think we need more math to fully understand neural networks?
I mean, do we need more math to understand the brain is the question. I think both of these fields are evolving at the same time in terms of math for AI and math for neuroscience. I think so, yeah, overall. But it's really exciting to see how principles of symmetry, right, equivariance, higher order connections in between neurons, like those are all pulled from neuroscience. And it's really cool to see that they work well in our field as well. So hopefully more math.
Yeah, definitely quite inspiring. And then another question, perhaps quite weird, is like, how long did it take you to write this review?
It's a good question. I mean, it was a huge team effort. So Sophia, I'm co-first author. The first co-author, Sophia, started writing it about 3 years ago when I was just starting out my PhD. And then I made all the figures, which took me about 4 months of full-time work. But it was a huge collaborative effort, and I'm really grateful to have a team that can pull this stuff off.
Okay, cool. Thank you. Yeah, I think I don't have more questions. Let's see if we have some questions on the chat. Let's see. Okay, so there is a kind of generic question that says how to start researching about neural networks from scratch and whether a computer science candidate can do neuroscience research.
Mm-hmm. Like how to understand networks from scratch so that we can understand the brain from scratch, kind of? I'm not sure.
Not sure either.
Yeah, I mean, there's examples of this in vision. People who can train networks to do computer vision and then have collaborators that go and look in the brains of mice and can go and find, for example, the neurons that are responsible for head direction, preservation, and stuff. But I would say that for now, 99% of the research is in the other direction, where neuroscientists find cool things about how the brain works, and then we try and put them in machines, not the other way around.
Cool. Yeah, and there is a question from Alex, which is, what do you use to make the figures?
Adobe Illustrator. Highly recommend. It costs a little bit of money. I think my lab buys a subscription, but if you want to make pretty figures, ditch Keynote, ditch PowerPoint, use Adobe Illustrator.
Okay, thank you so much. All right, I think there are no more questions. I wanted to thank you personally for the paper and also the presentation. Like we've been learning some geometric deep learning for the past few months maybe, and definitely this helps a lot because it summarizes a lot of things and it directs us to which papers to read and so on. Thank you so much. Yeah.
Yeah, thank you a lot. I will stop the recording now, and then we will share the recording on YouTube, and everybody can access again.
Thank you so much, everyone.